This presentation, if you guys have attended other ones that I've done, this is going to be slightly different. Can you guys see that? I hope you can.
Yeah, it looks good.
Okay. This is going to be a little bit Takahashi style for those of you that know, but not entirely, because talking about code is a little bit difficult. I'm going to move some more stuff around here. Give me a sec. But we're going to talk about the state machine of enlightenment. This talk is mostly going to be about the OTP behavior, gen statum. And I'm really excited to talk about this. Alex and Abelino both know that I have been harping on about state machines probably for about a year at this point. I think they're an incredibly powerful tool and incredibly useful especially for nerves developers, but I mean, really anyone who's writing Elixir code should be able to understand and think about structuring, designing their code as if it were a state machine. So I'm really excited to talk about this. Oops, that's the wrong window. There we go. But first, before we get there, do we have any Lord of the Rings fans in the audience today? I am seeing, all right, I'm seeing a raised hand. I'm seeing a couple smiles. You guys have all seen the movies, I hope. And you remember how in the very first movie, at the very beginning, Galadriel kind of does that narration about the history of the rings and all of that, right? Like the rings for the elves and the dwarves and the men. And then she's like, but they were all deceived, for there was another ring made in secret by Sauron. Well, before I get to the state machine talk, I have deceived all of you here. I have even deceived Alex, mostly. And I have made another presentation in secret. So before we talk about state machines, we need to have another presentation first. And the title of that presentation is We Love GenServers. Let's all put our hands together for GenServers. Woo! All right. Now, we're going to start kind of from an interesting point when we're talking about GenServers. And the question I want to open with is, what's the purpose of a process? You're all muted, so I can't get any community interaction here. So I'm going to jump straight to the answer, at least what I think the answer is. The purpose of a process is to run code. The follow-up question to this is, well, what code does a process run? How does a process know what code it needs to run? How does it know when to stop running that code? All those really good things. And the process is told what to run for a vague definition of told. If you want to like really get down in there into like the ASM level, you can think about it as like the instruction pointer, and you've got function arguments on the stack and all that kind of stuff. But generally speaking, we can kind of abstract this in a way that's nice for us as Elixir developers. We can think of it as a message, right? Something sends a message to a process and it says, hey, I want you to run this piece of code. Now, where does that message come from? Well, there's kind of two options here. Either an external process can tell another process what code it needs to run, or that same process can kind of, in a loop, not like exactly recursively, but kind of recursively, it can tell itself, hey, I want to run this piece of code next. Great, we have run code. Awesome. Now what? Well, we have a couple of options. And we think of this in the message way, in the Elixir kind of way. We could respond to the message, kind of a one-on-one. You sent me this thing. I'm going to give you a response because maybe you're waiting for it. You could also think of it like in a broadcast kind of way, like a pub subby kind of thing. Maybe we send many messages to many recipients. Maybe we don't send messages at all. And it was the routine that we just ran was entirely for side effects. Now that's an option as well. We also have the option of waiting for more messages, for more instructions about code to write, or if the process wants, it could just die. There's no stipulation that processes have to run code forever. Some processes exist only for a specific purpose, and then they're done. No need to do anything more. And this kind of gives rise to what I consider the fundamental process loop. Processes receive a message, they run code based on that message, they may or may not respond based on the code that they ran, and they may or may not repeat this entire thing. You can kind of think of it as an REPL loop, but I just kind of wanted to do 4 Rs in a row because I thought that was cooler, and I think the question marks are a good addition as well. And from this fundamental loop is kind of where we get the GenServer, because the GenServer gives us useful tools really for implementing all steps of that process. All right, so let's go over some of it. The receiving part, well, GenServer does that under the hood. That's just an Elixir receive. How about running? Well, We're programmers. That's our job. We write the callbacks, and the callbacks run the code that we want them to run. If we feel like we need to respond to messages, we have GenServer calls for that. We have our handle call. We can also just use Elixir and send messages to whoever we feel like. And if we don't want to respond, the GenServer behavior kind of has that built in as well. Casts and infos are more designed with the intent that it's not expected that you send a response message. And if you want to repeat, well, that's the whole point of the GenServer is to do it forever. But also, if you don't want to repeat, you can just tell the GenServer process, hey, I'm done. You can stop. You can go down now. No big deal. We're finished here. So it kind of neatly wraps up and abstracts and handles kind of some of the nitty gritty details of these things for us. But it's not just the act of running code that GenServers lets us do. It also lets us store a blob of data alongside this process. Just pieces of code isn't enough for what we need to do as programmers. So we need data alongside that code to look at and to analyze and process and transform and ship parts of it off to other pieces of the system. And the GenServer convention is that we call that the state. Now, in my work in our code base, we usually make that specifically a struct. You don't have to. The state is just whatever data you want it to be. And whenever the GenServer hits one of your callbacks, it's going to give you the data that you gave it. And it's good to have this code and good to organize it. But, we also want to think about, well, how do we control which pieces of code we run? How do we control when we respond, what we respond with, whether handler A runs or if handler B runs? So let's kind of go through some of how we can implement a little bit more control flow kind of stuff with our GenServers. So let's say that we want to guard our callbacks. We have a specific callback that we only want to run, when condition A is satisfied. That's pretty simple. We have our handle call and our arguments, whatever, and then we guard it. We just say when state dot condition. All right, that's not too bad. Pretty good. Looking good here. We can also delay a reply. This is obviously specific to GenServer calls. But if we get a GenServer call incoming, we can store that from data. And at a later point in time, we can use GenServer.reply to give the proper GenServer formatted reply without it being an explicit return to the handle callback. Which is pretty convenient. So, we have a little bit of leeway. Maybe we need to wait for something, or maybe there's a little bit of extra processing that we need to do. And so we kind of shuffle that off into its own functionality. Maybe it's common and multiple things need to use it. So there's some good options here. That's pretty nice. And if we wanted to, we could delay many replies. This is a pattern I've seen in some pieces of code. Whereas here, we were just storing the single from. You could imagine we have an enumeration of froms, maybe a list. I don't know, maybe you need a map or something. And so we do something like this. We have a list of all of our waiters, and we say for every waiter, we're going to give them a reply, and the reply is okay. And say, great, okay, so now even if many processes are waiting for our GenServer to do things, the GenServer can kind of go off and run its own code and figure stuff out, and it'll say, all right, everyone who was waiting, here you go, here's your response. A GenServer also gives us this good ability to have our own timeouts. And in particular, these timeouts occur if nothing happens. And what I'm referring to here is specifically the built-in timeouts in the GenServer behavior itself. And those are going to look something like this. So if we get a cast, the event is something, we're going to handle that event, and we're going to say, after 5 seconds, if nothing has happened, I want to generate this new event, and the contents of that event are timeout. And so if nothing happens to that GenServer within 5 seconds, we're going to hit our second handler here, and then we can do some other logic. Think about maybe if a connection has been quiet for 5 seconds, or if you didn't receive input from a keyboard or something like that. Maybe you want a timeout after some amount of time, and then do something special. However, there's a caveat here. And the caveat is that the built-in timeout mechanism for GenServer gets canceled anytime that process receives a new message. So if we still have our handle cast, we still set our 5-second timeout, but then I send a message foo to my GenServer. We are no longer going to get this timeout handler. That's not going to get triggered anymore unless the appropriate handlers all explicitly set that timeout timer, which they can do. There are questions there about maintainability, and if you have 50 handlers, do you really want to make sure that like they're all doing that? And we kind of start reaching some questions here of should we be doing this? What if we want to retry an event? That's another useful thing. Let's say that an event fails, and right, maybe we're trying to talk to a server and we're disconnected from the server, so we weren't able to complete it. Maybe we want to retry that event in the future. By itself, the GenServer doesn't really give you a built-in way to handle that. And there are a couple of ways to think about it. Here's one such way that you might do so. We receive an event and we attempt to handle it. If the event was successful and everything was good, then we say, all right, no problem. If the event gave us some kind of error, we can say, well, all right, it wasn't a good return, so here's what I'm going to do. The process is going to send itself a message after some predetermined period of time, and process send after is going to trigger the info handler. So this is kind of a self-sustaining loop. I tend to call it juggling a message, but there are probably other terms that work just as well. And maybe you don't want to do a send after. Maybe we want to cache this event in our state, and at some arbitrary point in the future, we can say, all right, let's rerun all of our failed events. And we're going to touch on that in a couple of slides, I think. So let's try combining some of these things. Can we guard a retry? Well, that doesn't seem too difficult. We have our handle info, and if a condition is true, then we're going to do the handling. But if that condition is not true, then we're going to juggle that message again. Or, we could cache it or some other similar thing. But importantly, we're not doing the handling here. We're just saying, yeah, maybe something's going to change in the future. And when it does, that's the only point where I want to actually do this event handling. And we can start to do some more interesting things here. We can combine GenServer replies with this idea of retrying as well. If a call fails, we don't need to explicitly reply error. We could give ourselves some leeway and retry that failed call. GenServer calls have a 5-second timeout, so we have to make sure it happens before then. Otherwise, things are going to blow up and no one's going to be happy. And if we're juggling things, we kind of have to use handle info. Technically, it is possible to spoof a GenServer call or a GenServer cast, but that seems a little bit out of scope and not something that you would ever actually want to put into your code base. So for the sake of sanity, we'll say you have to use handle info. And that kind of starts to feel weird, right? You end up with this design in your code where everything ends up as infos, because if you're trying to juggle the message, well, it has to come back as an info. So you end up doing a lot of send self. And there's another design question here as well. Isn't the whole point of Elixir and Erlang, isn't the mantra let it crash, right? So why aren't we just letting it crash? Why can't we just reply error? And that's a good question to ask as well. And we're going to touch on that a little bit later. We're building up, we're getting there. What if we wanted to retry many events? Well, we might have an Erlang queue, honestly, I think is the easiest way to do this, although you could use a list as well, no problem. If we have an event we want to retry, we're going to put it inside of that queue. And at some point in the future, we can have this neat little recursive function here, take the first thing out of the queue, handle it, and then we'll recursively continue going until our queue is empty. Now, there's some more logic here about maybe requeuing events if they fail again. I'm kind of brushing all of that to the side here. I'm leaving that up as a detail for you to implement if you choose to do so. But the idea is solid here, right? If something doesn't work, we'll hold on to all the things that don't work, and then we can decide how often we want to see, hey, is this thing going to work now? Now, can we guard retrying many events? Well, we could with multiple different guards. And maybe some of these events need to be replied to and some of them don't need to be replied to. And you start getting this deep into the logic, and the question is, well, how far am I going to write code like this, all of this scaffolding inside of my Gen server, just in order to handle the logic of what I expect to happen? That's my inner presentation. This is We Love Gen Servers. I'd like to thank you all for coming to this interior talk. I am not taking questions on this one because we have better things to do. And the things that we're going to do is we're going to get back to the state machine talk now. So the fact of the matter is that in physical reality, things go wrong. If you're installing a real system, like, I don't know, a smart doorknob or a smart thermostat, or you're trying to control a boat, things get messed up. Squirrels chew through wires. There are solar flares that, produce EM waves that scramble communications. And maybe the C library that you're using to talk over the wire has a quirk, right? Maybe the I2C bus is just super congested right now. And it's messy, right? It's a tricky thing to realize that the real world is not quite the same as the logic in code. And especially as nerves programmers, that's something that we have to realize. Nerve systems are not pure digital systems. We do not exist in the world of the purely abstract, where it's nothing but logic. We have to touch dirty, filthy reality, and things get broken. Sometimes checksums don't line up, right? Sequence numbers get out of order, and we don't know what to do with these things. We sit at the border between that real world and the nice, pretty digital world where all the rest of the programmers get to pretend that everything is perfect. And in my opinion, that's kind of where Let It Crash starts to run into some issues. Because if a squirrel has chewed through your communication wire, it doesn't matter how many times you let that thing crash, your supervisor is going to go down, your application is going to crash. Or if it doesn't, it's going to be left in a highly inoperable state, and you're not going to be able to do the things you want to do. And then clients are going to say, wow, why aren't we getting communications from this thing? Well, you see. And that's the thing about Gen servers. Gen servers work at their best the less we have to ask, well, hold on, what if this happens? What if X, Y, and Z? What if this message arrives before this message? What if this particular piece of communication fails, but it doesn't fail in 0.3 seconds? And it for the Gen server code, you start having to implement a lot of application logic, a lot of what I would call pure Elixir code. You're manipulating lists, you're interacting with queues, you're checking guard conditions. None of that has to actually do with the application that you want to write and the functionality you want to implement. It's just you wrangling Elixir to make sure that the right code runs at the right time. So what can we do about this? Well, we have this wonderful tool straight out of the OTP, and that is the state machine. Now, GenStateM is an OTP behavior that models a state machine. Some of you may have encountered the term state machine. In my opinion, the GenStateM is almost synonymous with a Turing machine. It is, frankly, the fundamental model of computation, in my opinion. And the saying goes, if a Turing machine can do it, any computer can do it. And that's kind of the power that state machine gives you at your fingertips, mainly through more extensions and more built-in functionality than the Gen server has. At its core, it is still the same receive, run, reply, repeat loop. I think I got that right. In that regard, it's the same thing that a Gen server is. However, what it adds, the main thing that it adds compared to Gen servers, is all of your callbacks have an extra datum. It can be any piece of data. Traditionally, it's an atom, and there's a reason for that, because under the hood, the state machine is going to use an MFA with apply to run your functionality. And so having your state as an atom can make that quite nice. But the point of this datum is that it represents the current state that your process should be in. And your process can transition from one state to another state. And ultimately, you organize your handlers based on whatever that current state is. So the state machine gives you two types of callback functions. One of them is the state name, and the other one is the handle event. Now, I say state name. Really, what I mean by that is something like this, where the name of the function is the name of the state. If we compare that to the handle event function, basically, we can see what happens here is that this argument 3 gets applied as the F part of an MFA, and so it kind of just becomes your callback name. But functionally, these are identical, mostly identical. And through the rest of this presentation, I'm going to use the state name callback style, but recognize that there's really no difference between the two. Compared to GenServers, the event type is going to be your call. That's your cast. That's your info. And then this is what you would consider your first argument in a GenServer callback. And that's going to be useful. We're going to see how this is useful a little bit later on as well. So handle event, the main difference between it and the state name callbacks is that you can have non-atom states. This allows them to be more complex. It's extremely powerful. You have to be very responsible with it. You could have your state be a list if you wanted it to be. It could be a tuple of whatever. It could be a map. It could be some struct that's 5 modules deep in your system. One thing that it does do, if you imagine a tuple of multiple states, is that you could have multiple state machines running in a single module, right? Each element of that tuple is the state of one of your state machines. So if you have like 3 elements in there, you could have 3 state machines running at the same time. Now, you might run into the question of how many callbacks am I going to have to write to make that possible? And that's your problem. That's not my problem. And the return from this callback is from these callbacks that the statem exposes to you is not just for the purpose of potentially replying to any callers, but also it directs the state machine to transition to new states. So what does that look like? So if we are in our first state and some callback gets fired, I don't really care about the contents for the purpose of this example. But what we're going to do in our return is we're going to say, I want to transition to the next state. And the state that I want to transition to, I'm arbitrarily saying that it's second state. Alternately, in my return, I could say, I don't want to transition. I want to stay in first state. So I'm going to keep my current state. And just like GenServers, we're going to return our data blob. Notably, by convention, this is now actually just data because we have pulled the state part out of it compared to GenServers. There's another very useful configuration option that we get, which is the state enter callback. This is entirely optional, but what state enter will do for you is it gives you another handler that runs only specifically when we go next state, and next state is different. So what does that look like? Well, if I am in first state and I enter it for the first time, I can do some one-off tasks that I might need to run. And then at that point, I can say, okay, well, I'm still going to be in first state. Actually, as a rule, enters are not allowed to transition to other states. So you kind of have to keep your state here. And then in the future, first state is going to get some other kind of event. And when we're handling it, we could decide that we want to repeat first state. And if we say repeat state, then we will actually pretend as if we have retransitioned and we will get this enter handler to fire again. However, keep state would not fire it. You could imagine it in an extra convoluted way, right? You could add like an intermediary step to make this happen. And this just kind of cuts out some of that crufty stuff. Alternately, if we don't want to repeat first state, we could say, all right, well, I'm going to go to second state now. And the moment that this gets returned, the next piece of code that runs, regardless of what's in the mailbox, regardless of anything else, is going to be the enter handler for second state. And you can do whatever you feel like doing there. In this case, we're doing nothing because it's just an example. But that's not all. There's more. There's always more. In addition to these transitional powers and our new friend state enter, we have more actions that we can do on return. So GenServers let you set a single timeout. It's an event timeout is what it is. And you can also do things like You can do the continues, which is basically similar to the enters. It kind of fires immediately. And you can also hibernate the GenServer, which I don't know if anyone's done that ever. I'm sure people have. So what are some of the actions we can do with the state machine? Well, unlike GenServer, unlike GenServer, our reply happens as a state action. It's not kind of like built in. So if someone does like a state machine.call, we have to add that reply to our state actions. And like all of these events, we can put as many of these as we want, because this is a list of actions. So the list of actions will run in the order that we put them in, that we structure them. And if it's possible to run them all, it will run them all. So we can have as many replies as we feel like. And we have another event. We have another return action called next event. And this is pretty similar to GenServer's continue. It inserts new events that run immediately post callback. So again, it doesn't matter what's in the mailbox or not. This is just kind of a way to help unblock our process a little bit. And different than GenServer continues is that we can specify the event type. So if you remember a couple of slides ago, how I was talking about the event type was our GenServer casts, our calls, our infos, those kinds of things. There's another type of event for specifically internally generated events. We can have a special flag that says, yeah, this next event was added as a result of this actions. And we can also timeouts are also included in these events. So what that means, well, we'll get there in a second. So if we're in first state and we get some kind of event, again, it doesn't really matter what we do with it here, but we are going to add in our actions here, we are going to say, actually, I want to insert another event. The type of this event is going to be internal, and the contents of this event are going to be foo. And so now this next handler will run immediately before anything else gets the chance to do anything. So this is very much kind of like the GenServer continue behavior here. We can do our foo things, and maybe then we decide that we want to move to a second state. We can insert as many events as we want, right? This is a list. We can put as many of these tuples as we want inside of this list, and they will all get in-queued and they will all run in order. Now, I don't know off the top of my head if we decided to insert events in our internal handler. I don't know how that would resolve as far as order goes. That's also an exercise for the viewer. Please experiment and find out. Let me know how it goes. But it's more than that, because you can spoof casts, calls, infos, timeouts. It's not just internal events that you can make up. So here I specifically said internal. I very well could have said info. I could have said cast. And then here in this handler, this wouldn't be internal. This would look just like a pre-existing cast, info, call handler that might have already been written. And so if we compare that to the message juggling that I kind of mentioned before with the GenServer things, we get around that because it's a lot more built in. Instead of having to like fake the structure of a GenServer message, it's just we just get to specify the event type, and it's already there, and it's so easy. So inserting events in the state machine gives us a lot more flexibility for which callbacks we trigger compared to the GenServer. And not just that, but the state machine gives us 3 types of timeouts, and they all serve very different purposes, and they are all very useful in their own ways. State timeouts are a timer. These are all timers, obviously. And the state timeout keeps running, and the only time that it cancels is when we say next state, and we actually move to a different state. Remember, by comparison, GenServer timeouts cancel the moment that any new message gets received. It doesn't matter what the message is. And GenServer has that as well. That's called an event timeout. So anytime a new event comes in, an event timer is going to get canceled. And then the final type of timeout is a generic timeout. Generic timeouts have names Maybe you can call them aliases, but I know that's a bit of a loaded term. But generic timeouts are named, and there is no automatic canceling. It is up to you as the programmer to decide if and when you want to cancel that. So it's kind of like process.sendAfter in that regard, but you don't have to keep track of the reference because that's already happening under the hood. And as long as you use the same name, then the state machine understands what you're talking about and it deals with it for you. So just as a simple example here, let's say we're in our first state and we get some event, don't care what it does. We're going to move to the second state. And at the same time, we're going to start a state timeout. And when that timeout expires, it's going to deliver this message. This could be anything that we want it to be. And that timer starts when we transition to state 2, to second state. So in second state now, we have this handler. Here is our type. Our type is timeout. We kind of knew that because it's a state timeout. And here's our message comment, our message contents, our event. And that matches what we said the event would be. And so if second state never moves to a third state or back to the first one, then after 10 seconds, it doesn't matter what second state has done. This is going to fire. And maybe we want a warning. Maybe we want to fail safe, transition to some other state. There are plenty of options here, right? But we have a guarantee that this timeout is going to trigger unless we get out of this state. And you can have these state timeouts either internally for the state that you are currently in, or you can set them when you move to a different one, like is demonstrated here. This is one example, right? We have three different types of state timeout. I'm not going to demonstrate them all. It's all very, very well documented. Please read the OTP docs. That obviously goes for everything that I've been talking about here. And having these three gives us a whole lot more control for our time-based events than we would have with the GenServer. We have more granularity about when we consider a timeout useful or not useful. We can start multiple timers all at one go without having to say like process send after, right? It's all just in our actions list. And the management of the canceling and the making sure all the references are correct, that's all under the hood. We, using the state machine module, using the behavior, don't have to worry about any of that. Whereas you can imagine like having a list or a map of like a bunch of timer references in a GenServer. I hope none of you have had to do that. And if you have, I'm sorry. I don't think I kind of have had to, and it's not nearly as fun as it might sound, and it already doesn't sound fun. There's one more. There's one more action that I consider to be the powerhouse. There are a couple of other actions as well, but like that's all in the docs, and it's all like a lot more esoteric stuff. But this is the great one for me, and it's postpone. Postpone is the powerhouse of the state machine, in my opinion. And postpone takes an event and it puts it in a queue. And any event that has been postponed is held onto, and it is run again in order because it's in a queue whenever the state is changed. And that, in my opinion, is the real power that the state machine gives us. So what might something like that look like? Well, let's say that we are in first state and we get a call, and the contents of this call are event 1. Again, I don't really care what it is, but first state is unable to deal with this event, right? Maybe this is disconnected from the server and we need to send a message to the server, right? Well, we can't handle that right now. So what we're going to do is we are going to transition to second state, and we're going to tell the state machine, we want to postpone this event. And then once we transition to second state, immediately, instantly, every event that we have postponed is going to get run automatically. The handlers get triggered without any intervention on our part other than we postponed it and we moved to the state. So now second state is going to get the exact same handler. It's going to pretend that it just received this event for the first time. And second state is capable of handling event 1. I don't know what it's doing, but like it doesn't matter. And we didn't have to keep track of who the from was. We didn't have to like keep a list of all the callers and all the waiters. It's a carbon copy of the exact same thing. And so now we can do our reply and say, great, everything's good. And there's basically no limit to what you can do with postponed events. I'm sure if you postponed an infinite amount of them, you would crash the beam and everyone would be sad. But as far as integrating it with your state transitions or maybe not your state transitions, no holds barred. You can change your state and postpone an event at the same time. You can postpone it while staying within the same state and waiting for something else to change your state. And the result of this is anytime you transition, they all get retried. And the cool thing about this is you can daisy chain it, right? I very well could have said here in second state, maybe second state is also unable to handle it. Well, that would have been okay. I could just postpone it yet again. And then when we go to third state, maybe then we're finally actually able to. So there's no limit to how many times you get to put something off. And whether or not you deal with it is entirely up to whether the state machine that you have defined is in the correct state to deal with it. So that's kind of an overview of the most important features in the state machine. So let's take a look at some practical yet still generic examples of what we can do with this kind of stuff. And as I'm going through these, I hope you guys kind of ask yourselves, how would I implement some of this functionality with a GenServer? Because chances are you're going to be thinking a lot about lists and popping things and stuff that's not your actual business logic. So here's a simple example. This is one that we do more or less have in our code base as a connection manager. Our connection manager is going to have two states. It's going to have disconnected and it's going to have connected. If the state machine is in the disconnected state, anytime any event arrives, it is going to attempt to reestablish its connection. It's kind of your choice whether or not you want to, what you want to do if that reconnect fails. You could give a reply back and say, actually, sorry, we for real, we tried, we're disconnected. Or you could postpone it and say, well, actually, we'll hold on to it and maybe we'll try again in 10 seconds. I don't know. But if the reconnection was successful, then we're still going to postpone the event so that we can retry it in a moment. And we're going to transition to our connected state. And in our connected state, now that we are connected, now that we know for a fact we are, we're going to utilize that connection. We're going to handle all of our events. If we were unable to successfully do a transaction, we will take that event and postpone it and go back to the disconnected state. But if everything went good, then we're still in the connected state. All is hunky-dory. So really, if we abstract away the business logic parts of it, we only need two handlers for this. Maybe a couple more. But if we're in the disconnected state and we get some kind of call, here's what we're going to do. We're going to try to do a reconnect using whatever our data is. And if we succeeded in that reconnection, we're going to postpone the current event and we're going to move to the connected state. If we failed at our reconnection, in this example, we're just going to tell the caller that, we're super disconnected from the server. It's not happening. Sorry, tough luck. And then when we transition into the connected state, now any postponed events are going to run. So this exact event happens again, but now we're in the state that we like. So we are now going to handle that event. And if we were successful at doing so, then great. We're connected. Everything's working. We're going to let the caller know that here's the reply. Here's the result of your request. And if it failed, well, maybe there's a reason why it failed. Maybe the connection timed out in the meantime. Maybe the other end of this connection decided to close the end of it for arbitrary reasons. Maybe Erlang did something under the hood and we don't really know. So just to be safe, we're going to postpone the event, which is going to cause it to run again, which is going to cause our reconnect to run again. And then all of the details of what we're actually doing that's business logic. That's handled in this handle function. Y'all can figure out what to do with that. So this very simple two-state machine here, for some connection libraries like GenTCP, for example, in one of its modes, it'll send you a message if the TCP socket gets closed. And you could pretty easily imagine having an info handler here, an info handler in the connected state that receives that socket closed info and automatically moves you to disconnected. So we don't even have to worry about this, and that's just managed by another handler. So the async messaging type of networking that Erlang and Elixir like to do, pretty easy to support that here. And now we have a really obvious separation of our application logic and our business logic, because the application logic is, 10 lines of code approximately, less if you discount the ends. And then we can do all of our business logic at this point inside of our handle function, and that's in one spot. And we could extend this to add extra functionality, extra ways to manage our connection status, right? We could start a state timeout on disconnect, and periodically, maybe every 5 seconds, we just automatically re-trigger the retry connection function. You could also do this with internally generated events. There are a handful of options here as well. Now, I will say, and perhaps some of you noticed, it is technically possible to get an infinite loop with the previous code. And the moral of the story there is be careful. Because here, for example, if the reconnection succeeds and then we try to handle and it fails, then we go back. And if the reconnection succeeds and we try to handle and it fails, you can technically do that forever. So you do want to be a little bit careful here with these types of things, but also exercise for the reader. So as one good example, let's think of another one. Let's think of a task runner. And maybe we have tasks that are computationally expensive and heavy to run, and we don't want to be running every single task as soon as it comes in. We want to kind of have like our own process scheduler basically going on here, right? So this one's also going to have two states. We have an idle state, we have an active state. When we enter the idle state, we're going to cancel any task that is actively running. And the idle state is going to sit around and it's going to collect requests for new tasks, but it's not going to start them. And after 60 seconds, the idle state is going to receive a state timeout. And in that state timeout, we will go to the active state. When we enter the active state, we will start all the tasks that we have collected. And once we've started them, the active state sits around and waits for them to finish. You can think about your strategy here for how you want that to happen. And after 60 seconds, the active state times out again. So basically, we have a burst of heavy computation load, and then we have another period of time where we step off the gas and we let other parts of the system, do more work as well. And then we go back to the idle state. So what's that going to look like? Well, we have a little bit more here because we have our enter handlers. So when we enter the idle state, we're going to look at our data and we're going to cancel everything that is actively running. How you determine that is up to you. And then you do nothing. And after a minute, we're going to trigger this state timeout. And the only thing we need to do here is say, all right, it's time to become active. And when we become active, we start all our tasks again, figure out how you want it to happen, and then do nothing. Sit around and wait again. And after 60 seconds, we kick ourselves back into the idle state, which is automatically going to run this enter. We automatically cancel all our tasks, and the loop just keeps going. And there are more benefits here than just this very simple state timeout, right? It would be very easy to switch states early. You could have an info message or a cast or something that triggers that state transition, and that state timeout automatically gets canceled. In a similar vein, you could extend the duration of one of those states if you wanted. If you set a timer that is already running, it basically restarts it without triggering the cancel behavior. So if you're 30 seconds into the active state and you say, oh man, I need more time, you send a message that says extend, and it'll reset the timer to 60 seconds. And now you have a minute and a half, right? And in the meantime, if we imagine this is task.async or something, the state machine still collects new tasks and the timeout is not lost. And you can do that with a GenServer, but you have to manage the timer ref yourself. We don't really have to do that here. It's just a part of the system. One more example, an enforced setup progression, an enforced configuration startup routine, kind of. So here for this example, we have a strict order of execution. We have multiple states that we need to go from A to B to C, and so on and so forth. In this example, we have 3 states. We're unconfigured, then we're unscheduled, and then we're finally running. And at any of these states, If the state machine does not fulfill the requirements for the transition, then it doesn't move to the next state. And if the state machine is still early in the sequence, it will postpone messages that that state is unable to deal with yet. We don't want to lose those events, but at the same time, the state machine is aware that it's just not prepared yet. So what's that going to look like? This is going to be a couple slides. So in our unconfigured state, when we enter it, we are immediately going to kind of GenServer continue style. We're going to trigger our do config internal event. And the only reason we have to do it like this is because on enters, you can't transition state. That's fine. So we trigger this internal do config routine. And if our configuration was able to succeed, then we will move on to the next state. If it was unable to succeed, we're going to maintain the current state. And you can imagine ways to trigger a retry of this routine. Plenty of options here. External events, internal events, state timeouts, all the fun stuff. However, if we do end up staying in the unconfigured state and other events come in, events that we don't want to, that we don't even have our thing configured yet. How can we handle any of this? Well, we're just going to hold on to it and postpone it for later. But let's say we were successful. Great. We managed to move on to the next state. Okay, so we're unscheduled. We're going to have this same mechanism of doing our try to move out of the state routine. So we're going to say do schedule, and we will do our best to apply whatever the schedule stuff involves. And it's the same pattern here. If we succeeded, we move on. If we failed, we stay in the current state. And now we've added an extra handler, because at this point, we have a specific thing that we might want to do. If for some reason we need to redo our configuration step, we can have one specific handler that the unscheduled state knows how to deal with. And that's going to move us backwards to the state that we were just in and kind of try everything all over again. And for anything else, again, we're not scheduled. We're not prepared to deal with these things. So we're just going to put them off until later. And I believe I have omitted the active state because the active state is insert your business logic here. Do whatever stuff you need to do. All of the events that you have postponed will run, importantly, in the same order that they were postponed. So it's kind of like doing a little bit of fast forwarding through time, pretty much, with the goal here being that once you've run through all the postponed events, you should be up to date on the correct way, that the correct state, I guess, of the state machine based on handling things in the actual order they came in, just much quicker because it's all at once. Right. And so we could, if we wanted to, we could add some timeouts to periodically retry our states. You could have like a special info or a special cast to notify. There are options there. And now we get to automatically store/juggle our messages until we eventually reach a state where any arbitrary message, any arbitrary event is actually able to be handled. And with our heavy-handed application of postponing here, there are no weird message races, right? Perhaps you're subscribed to a topic and that topic happens to that publisher pushes a message out to its subscribers, right? And it does that very early on, earlier than you were expected. And you don't have to worry about that because we were very generous in all of the events that we postponed. Now, if your sequence of states here is simple, right? Like maybe this is overboard, right? Maybe you can use a GenServer and like it's okay to have a simple guard or two on your functions. However, we live in nerves land. Nothing is simple. So let's go over a quick little recap here. What have we learned? For complex scenarios, GenServers tend to require a lot more application logic, a lot more pure Elixir code. Now, nerve systems tend to touch other systems that are impure and have lots of complex scenarios, lots of unexpected events. And sometimes the only way to resolve those complex scenarios is with time and with patience. And letting it crash could take your supervisor down in 100 milliseconds because, you tried to talk over the I² seed line and the I² seed line is just super congested right now. Maybe let it crash would fail because it's going to take 2 days for a technician to get out to the site and replace a wire, that's connecting your communication lines. Maybe the DNS server is down, and so you can't resolve things. Maybe there's a solar flare. Any number of options. Maybe maybe someone walked by and pointed a laser at your camera, and it produces this super weird output that no one expected. And by comparison, GenStatum gives us a lot of conveniences for manipulating and maintaining and managing our current state of execution. It's really, in a lot of ways, an extension of existing GenServer features, but you get more flexibility. You get more options about what you want to do for some specific thing, right? You can spoof calls and casts, which can be super useful for cutting down the number of handlers that you need to write. All sorts of things. When it comes to state machines, the only limit is yourself. I encourage all of you, please go to the OTP docs. They have not only like the literal module documentation for GenStatum, but they also have like it's called like GenStatum behavior document or something, and it talks about like best practices, how to actually use the GenState machine to accomplish the things that you want to accomplish. You could spend days reading that thing. I probably have at this point. And there are some features even beyond what I've discussed here that offer you even more power that, frankly, I'm too afraid to touch. You can do anything with state machines. They really are, in my opinion, they could rename it to Gen Turing Machine, and that would be a perfectly accurate name as well. It really is whatever you feel like. And the organization, in my opinion, is a lot cleaner to read and to manage and to extend, as you get more features and more functionalities, and as your code base gets more complex, because there's no such thing. Code bases move through time and they get more complex. They never move through time and get less complex. So it's something to always consider. Is how easy is this going to be extended in the future? And the state machine, in my opinion, makes it significantly easier compared to just plain old GenServers. And that is the state machine talk. I hope you all will one day reach your own state machine of enlightenment. I'm fairly far along the journey, but Nirvana is still a little bit out of reach. And now I will take questions. So if you got them, fire them off. I will ask the question that I was expecting to get. How about the Gen State Machine hex package? Because it's out there. There is an Elixir package called Gen State Machine, with all caps, and it's nice and Elixir-like. Why don't you use that? Why are we talking about this OTP behavior? And my answer to that is that this Elixir hex package is literally just a syntax wrapper. In fact, it leaves out a couple of more advanced callbacks and functionality that GenStatum has, while offering nothing on top. So just use the OTP version. It's literally a syntax change.
So every time I've ever talked about state machines, people get really excited and they want to see an UML state diagram. Have you tried any kind of tooling to diagram your state machines with that?
Yeah, great question. So at GridPoint, whenever we do this, we have a design meeting once a week where we kind of go over, whatever things we think we need to design. And whenever it's my turn to talk about state machines, the Lucid link comes fast and furious into chat. And it's pretty much exclusively through Lucid. I'm sure that there are like more professional like tools that are designed for doing this sort of thing. But yeah, have your circles, have your arrows, label those arrows for your transitions. Yeah, it really helps to lay things out like that. Yeah, circles and arrows, exactly. That's all it takes.
Learn plant UML and find a nice xdoc macro that can generate stuff for you.
Ooh, that's a great idea. Yeah, embedding it directly within your documentation. Yeah, I love the sound of that.
So Ben, there
Yes.
something that might be important here, and that is, well, what if we have more than a handful of states and more than a handful of callback implementations for those states?
Great
Is there
question.
something in GenStatum to help organize the code so that you don't have this massive file, massive module at the end of the day?
Mm-hmm. That's a great question, and thank you for guiding me in this direction. This is mentioned and discussed in the GenStatum behavior documentation, and what they recommend that you do. So, for example, if you have a message that matters in one specific state, but you have 10 states total, right? You don't want to rewrite the same generic handler for all 9 of the other states. And so, what they recommend doing in the behavior docs is, well, they have 2 options, but basically it comes down to a handle common function. And handle common is more or less your siphon for things that you don't care about or for things that you know are going to be shared between multiple states. They suggest an Erlang macro to do it, which is one option, but they also show a way to implement it just as a regular old private function that you use regularly. And so, yeah, so if you have something that really only matters in a small number of your states, the best plan, in my opinion, and apparently in Erlang's opinion, is to have just a single kind of catch-all function that all of the other states just funnel into. And you can make that handle common as abstract or as specific as you want it to be for the specific things that you think you need to handle. You have, many implementations of it.
But in a complex state machine where each state might have um, a variety of implementations, a variety of callbacks, that still leads you into in the direction of, well, in the end, you're going to end up having a rather large module.
Mm-hmm.
There
So
is something in GenStatum to help with this. I'm wondering if you've run into it.
if so, I either haven't ran into it or it is eluding me at this exact moment. What are you thinking of?
So there's something called change callback module.
Ah, yes. Okay. Yeah, that was some of the advanced functionality that I was thinking of. Yeah. Please talk about it. Go for it.
So and this is something that I've used in the past on a firmware application where the firmware required or had more than a handful of states. And each one of those states had more than a handful of callbacks very particular to that state. So if I would have shipped all of that in a single module, I would have, I don't know, maybe um, a rather large file with upwards of more than 25 callbacks um, in that single file. So in GenState M, the change callback module allows allows the developers to split out the sets of callbacks for each state into their dedicated modules. So now you could have your own module um, for commissioning versus decommissioning or whatever those states may be. And this, because you're splitting out the callbacks for each of one of those states, um, one, you're helping with code organization in your project. And two, it makes it much easier to run through the one little file versus trying to find your spot in a rather large file. And the rest of the mechanics of GenStatum apply. Nothing really changes in terms of how messages are postponed, how messages are juggled. It's just that the next set of callbacks that are going to be used for the next state you're going into are defined in a separate module.
Yes. Yeah, that is a very useful piece of functionality. That's one that I haven't personally used, but I definitely see a lot of value and power in using. And it's also coincidentally something that the GenState machine hex package does not let you do. So, yeah, more arguments for just use the OTP. Alex, questions, thoughts? angry exhortations?
I do have one, but first of all, I'm wondering who else. So Abelino mentioned using state machines, GenStateM. Who else has used GenStateM in a project before? Okay, pretty new to the audience then. Well, cool. Hopefully this gives you some stuff to play around with then. Ben, my question is really what your next talk is going to end up being about. It's
Goodness.
tangential. It's
Yeah.
tangential to state machines, but you picked on it several times in the presentation, so I'm just going to have to go there. And that's let it crash.
Let it crash. Yeah. I think that's a good topic, especially for the nerves crowd, and potentially to bring outside of the nerves crowd as well.
My controversial point is I don't think you've quite nailed it yet.
I would agree. I don't think it's perfect just yet. But I think that the way it is right now touches enough nerves, pun intended, not intended. It touches enough nerves to bring up some good discussion, which is also very valuable.
Yeah. And there's, just to throw it out there, you did call out how, especially in nerve systems, I see this in a lot of Elixir code, but it is definitely, I'd say, more prevalent in nerves. Let me back up and say, I think the philosophy behind let it crash is really around avoiding defensive programming. And you coming from the C background can probably relate to what that looks like of everything's wrapped in an if statement. You're always checking return values of every single thing along the way. If you've ended up with a null pointer that came out of something or some failure return code or something like that, you need to make sure you handle every single case and you have a lot of code around the failure cases and potentially a lot more code around failures than you do having your actual bit of work that you're trying to do. So there's, I think, kind of the essence of let it crash is really around the defensive programming side of things of look how with Erlang and the Beam and this whole ecosystem, you don't have to be as defensive in your application code, or you shouldn't have to be as defensive in your application code because the Beam has mechanisms to help handle that for you. In practice, which is what you're touching on, there are some legitimate scenarios out there. Actually, there's a lot of use cases out there, and connectivity is one of them that you touched on, where being disconnected is not a failure crash state. You should not crash because you're disconnected. But that's one of the things that I've seen it tempting for people to do and write code around where you'll do a hard pattern match on like OK and whatever your handle is for your connection. And if you don't end up in a connected state, you crash that process because you did a hard pattern match on it. And that's not what you should be doing, and that you shouldn't be crashing in that case. But like you showed with the state machine logic, you also shouldn't have to write a ton of defensive code around it. It's about finding the right tools for the job, state machine being a great one in that case, of use a state machine and no op when you're disconnected, or postpone your messages, or push that stuff off till later, till when you are connected. And it doesn't have to be a ton of code to write that, or like you just showed off, you can pass that stuff off to the Beam. So I think the community in general has leaned in a little bit too hard into let it crash into places where you really shouldn't be crashing. And I think that's starting to give let it crash a little bit of a bad reputation. But just to throw that out there, I think it's more about the defensive coding aspect than literally when you crash and when you don't.
Yeah, that's fair. That makes a lot of sense. Yeah, right. If it returns an error tuple, you should probably be prepared to receive an error tuple as your return.
Yeah, like it's telling you something. And that's actually a good reason of why those errors are returned like that, and you're not having to do like catch, raise, rescue type stuff in Elixir, because it's a lot easier to throw away an error response that way if you don't want to handle it, if you want to no op on an error. If you do need to care about it, you can do something and handle it. Well, that's not a lot of the code that I see in the wild. It's hard pattern match on OK, and then things blow up, and then people wonder why the program's not working right.
And speaking of things blowing up, this is something I didn't mention in the main body of the presentation. GenServer timeouts default to 5 seconds. Gen state machine timeouts default to infinity for calls. And there is a lot of benefit to that. There's also potentially danger, right? You can't tell if something's deadlocked or if it's just waiting for a very long time. But especially for NERSC programming, where we're touching real physical systems and sometimes real world time is needed, 5 seconds doesn't cut it. And having that infinity built in by default is a huge blessing, because GenServer timeouts, in my experience, have been a very common source of unexpected crashes, because things just take a little while sometimes. And trying to be defensive about that with the GenServers is an exercise in futility. Not fun. Do not recommend.
That's also a great point for anybody up in Phoenix land or interfacing with a web server, because those connection timeouts, it's like a default 60-second timeout when you're working with a web connection. And that will absolutely time out your GenServer requests. And so, this is a really good point on state machines. So basically, if you're working with connectivity, you might want to be looking at reaching for a state machine first, because this can really help solve a lot of those connectivity issues.
So is there a way to find out when too many events have been postponed?
I imagine like something beam related crashes. I don't know if it gives you warnings about that, other than whatever mechanisms might already be provided. I imagine it would take a lot though, but
if those are getting queued up as messages, you should be able to find those by looking at the observer. And that will be able to show you the process and how many messages are in its mailbox. So you'll see those filling up.
Although I don't know off the top of my head if postponed messages are actually stored in the mailbox like that. I think they're just cached in memory until a state change happens. But that's under the hood. I could be wrong.
That'd be interesting to see. So I look forward on the follow-up to this presentation of where you go into the performance of GenStateM and everything it does under the hood.
I'm pretty sure that one is just called read the source code, which everyone can do that for themselves, right?
Read the Beam book, which seriously, that one's not a joke. There actually is a website called the Beam book that talks about a lot of the internals of the Beam. Very good read for this type of stuff of how the internals work. Ben, it sounds like you've either given everybody a lot to think about or you've completely baffled everybody in the audience. So either way, mission success.
I hope to see a surge and uptick of state machine formatted code in the near future, or in the not so near future. It takes time to digest, but looking forward to it.
Cool. Well, thanks, Ben, for this talk. This has been great.